Let's talk about a theory that says reality isn't quite what it seems. It's the engine behind your smartphone, it's how medical scanners work, but at its heart, our ideas so bizarre, they defy common sense. We're going to try to make sense of it. This is the story of quantum mechanics.
So yeah, let's start with a little bit of humility, okay? This comes from Richard Feynman, one of the absolute giants of the field. And he wasn't being coy. The ideas we're about to jump into are notoriously strange, and they really do challenge everything you think you know about how the world works.
And yet, and this is the incredible part, for all its mind-bending weirdness, quantum mechanics is probably the most successful scientific theory in history. I mean, its predictions have been tested and proven to a ridiculous degree of accuracy. It's the foundation of everything. So how can we not understand something that works so perfectly? To get to the bottom of that, we have to follow the story. So here's our roadmap. We'll start when physics was hitting a wall. Then we'll see how this radical new idea came to be. We're going to unpack its bizarre new rules, see how they literally built our modern world, and then we'll get to the big one. What does any of this really mean?
Okay, so let's rewind to the turn of the 20th century. Physics was feeling really good about itself. You had Newton, you had Maxwell. It all seemed to describe this beautiful clockwork universe where everything was predictable. But the closer scientists looked, the more they found these little puzzles, these little glitches in the matrix that their perfect theories just couldn't explain.
What they were finding was like a tale of two different universes. You have the classical world, our world, right? Planets, billiard balls, everything is smooth, continuous, and predictable. But down at the scale of atoms and particles, in the quantum realm, the rulebook is completely different. Things happen in these sudden, discrete jumps, and absolute certainty just goes out the window, replaced by pure probability.
And the cracks in that old classical foundation were getting bigger. For example, the old theory said a simple hot object should be blasting out an infinite amount of energy, which it obviously doesn't. They couldn't explain why light had to hit a certain frequency to kick an electron off a piece of metal. But here's the real kicker. According to their own laws, every electron in every atom should have spiraled into the nucleus in less than a second. All matter should have collapsed. So yeah, physics was broken.
Clearly, something had to give. A revolution was coming. And it didn't happen all at once. It came piece by piece from a whole new generation of brilliant, brave physicists who were willing to say, you know what, maybe the old rulebook is just wrong.
And things moved so fast. It all kicked off in 1900. Max Planck had this wild idea. What if energy isn't continuous? What if it comes in these little packets he called quanta? 5 years later, a young patent clerk named Albert Einstein runs with that idea and says, hey, maybe light itself is made of these particles, photons. By 1913, Niels Bohr used the same concept to build a model of an atom that's actually stable. And then, in the mid-1920s, it's just this explosion of progress from people like Heisenberg and Schrödinger. And suddenly, we have the complete mathematical theory we still use today.
So the math was beautiful. It worked perfectly. But the picture of reality it painted, it was stranger than anyone could have ever prepared for. It was time to learn a whole new set of rules about how reality itself behaves.
First up, and this one's a doozy, wave-particle duality. The idea is that something like an electron isn't really a particle, and it isn't really a wave. It's both at the same time. If you do an experiment and don't look, a single electron will act like a wave going through two places at once. But the instant you try to measure which path it took, poof, it snaps into being a particle in a single spot. It's as if its very nature depends on us looking at it.
Then you've got a fundamental limit on what we can even know about the universe. It's called the Heisenberg Uncertainty Principle. And it basically says you can know exactly where a particle is, or you can know exactly where it's going, but you can never, ever know both at the same time. And this isn't a problem with our measuring tools. The universe itself has a built-in fuzziness that we can't get past.
So how do scientists even deal with all this fuzziness? They use something called the wave function. You can think of it as a cloud of possibilities. It doesn't tell you where a particle is, it just tells you all the places it could be and how likely each one is. Before you measure it, the particle is in what's called a superposition of all those states at once. And the math that describes how that cloud of possibility evolves and moves, well, that's the legendary Schrödinger equation. It's the master key to the quantum world.
Now, I know what you might be thinking. Okay, this is some really weird, philosophical, abstract stuff, right? Wrong. These aren't just thought experiments. These bizarre rules are the actual blueprints for almost all of our modern technology.
Seriously, its impact is just everywhere. Lasers work because of electrons making these little quantum leaps between energy levels. The tiny transistors in your computer, that's all quantum behavior of electrons. MRI machines,
They work by manipulating a purely quantum property called spin. And the next big thing, quantum computing, is literally built on harnessing weird concepts like superposition to solve problems we can't even dream of tackling today.
So there's no question that the theory is a massive success. It works. It powers our world. But even after 100 years, the smartest people on the planet are still arguing about what it's actually telling us about reality. What does it all mean?
And this right here is the heart of the whole mystery. It's called the measurement problem. The math, the wave function, it describes this ghostly cloud of probabilities. But every single time we go to look at it, to measure it, we only ever see one single, definite thing. That cloud of possibilities seems to collapse into one reality. Why? What's so special about a measurement that makes reality snap into focus?
Honestly, nobody knows for sure. There's no scientific consensus, just a bunch of competing ideas. You've got the classic Copenhagen interpretation, which just says, look, that's how it is, the measurement makes it collapse, don't ask why. Then you have the wild many worlds idea, which says it never collapses. Instead, the universe splits into parallel timelines for every possible outcome. And there are others, like pilot wave theories, that say there are hidden variables we just can't see. They all just trade one mystery for another.
But don't think for a second that this story is over. Not at all. We might be right at the beginning of the next quantum revolution. Because physicists aren't just scratching their heads at the weirdness anymore. They're figuring out how to use it.
The new cutting edge is something called quantum information science. And what's happening here is a huge shift in thinking. Scientists are taking the strangest parts of the theory, like entanglement, this spooky connection between particles, and instead of seeing them as confusing paradoxes, they're seeing them as powerful resources. Resources for building new kinds of computers, new sensors, new ways to communicate.
And that leaves us right back where we started, with a really deep question. Quantum mechanics tells us that underneath it all, the fundamental fabric of reality is just this shimmering world of probability, uncertainty, and ghostly possibilities. So if that's the real foundation of everything, how in the world does our solid, predictable, common-sense world emerge from it? That mystery, that's the great adventure that quantum mechanics is still taking us on.